In this video, we're going to look at applying the integral estimation theorem to a particular example. So here I have the series, that's the sum from n equals 1 to infinity of 1 over n to the fourth. And my goal is going to be to try to estimate the sum of that series using a particular number of terms and then be able to say how good that estimate is. So first I'm told to find the partial sum S5 of the series. So notice that S5 here would be equal to the sum of the first 5 terms. So this would be 1 plus 1 over 2 to the fourth plus 1 over 3 to the fourth plus 1 over 4 to the fourth plus 1 over 5 to the fourth. Okay, that turns out to be about 1.08035. Okay, but now I'd really like to know how good is that estimate. You know, depending on what I might want to be doing with this sum in some application, maybe that estimate would be good enough, but I'd want to be able to say something about the bound on the error between that and the actual value of the sum. So our goal is to estimate the error and using that as an approximation to the sum. Well, remember that when we're talking about the error, we're talking about getting an estimate on the remainder. Okay, and if we want the remainder in using S5, then we're talking about getting some bounds on R5. Okay, so remember R5 would be equal to S minus S5 here. And we know that our remainder is bounded between what values? Well, it's bounded between n plus 1 to infinity. So in this case, that would be 6 to infinity of f of x dx. And less than or equal to the integral from n to infinity, or 5 to infinity, of f of x dx. Okay. Usually we're primarily concerned with the upper bound because it's generally more useful to say that we know our error is definitely less than or equal to something, but sometimes we'll want to use that lower bound information as well. So here we'll just start with finding the upper bound. So we know that R5 will be less than or equal to our integral from 5 to infinity of our associated function. So notice that we're dealing with this sum from n equals 1 to infinity of 1 over n to the fourth. So f of x will equal 1 over x to the fourth. Okay, so that f of n is equal to 1 over n to the fourth, the terms of our particular series. And we'll go ahead and just assume this meets the conditions of our integral test. This is a positive, continuous, and decreasing function. So we can focus on the computation here. So this is 1 over x to the fourth that I need to work with. So notice that what I have to compute here is an improper integral. So I'll need to find the limit as b goes to infinity of the integral from 5 to b of 1 over x to the fourth dx. So I'll have to take the antiderivative of that. So 1 over x to the fourth would be x to the negative 3 over negative 3, okay, or 1 over negative 3x to the third, okay, and this is evaluated from 5 to b, okay, so this gives me the limit as b goes to infinity here. This will be 1 over negative 3b cubed minus 1 over negative 3 times 5 cubed. Okay, notice that'll give me plus a positive in there. As b goes to infinity, this 1 over negative 3b cubed will be going to 0, okay, because that denominator will be getting very, very large. So we see that our limit comes out to this 1 over 3 times 5 cubed. Notice that 5 cubed is 125, so this will be 1 over 375 is the upper bound. Okay, so here we can say that, so the error in estimating S, the sum of the series, by S5, the sum of the first 5 terms, is less than or equal to 1 over 375. Okay, so that's a pretty decent approximation. So let's just look at one step further we could do with our estimation theorem. Okay, so we're given this inequality here. Where did this thing come from? Remember that Rn is between n plus 1 to infinity of f of x dx and n to infinity of f of x dx, the integral from n plus 1 to infinity here and the integral from n to infinity here. Okay, and again we know that our Rn is equal to s minus Sn. Okay, so notice that means that s is equal to the remainder plus the sum of the first n terms. So if I just add Sn to each piece of this inequality here, I get this statement here. So this is an inequality here that gives me an upper and lower bound on the actual value of the sum. So if I do Sn plus n plus 1 to infinity as the lower bound and Sn plus n to infinity of f of x dx for the upper bound here, that gives me an upper and lower bound for the actual sum. So let's see how we can get some bounds on our actual sum in this case. Okay, so notice that we have n equals 5, so we're looking at s5 plus the integral from 6 to infinity of f of x dx will be less than or equal to s, will be less than or equal to s5 plus this integral from 5, oops, I wrote 8 over here, vertical infinity. Okay, so I have infinity, infinity here, and this is f of x dx. Okay, so notice that we already figured out what this was. Okay, that was 1 over 375. If we had gone through that same integral here and just had a 6 wherever I have a 5, notice that my final answer would have come out to 1 over 3 times 6 cubed. So we can say that this is s5 plus 1 over 3 times 6 cubed is less than or equal to s, is less than or equal to s5 plus 1 over the 3 times 5 cubed that we found before. Okay, so using our estimate, we can now say the value of our sum is between the following values using a calculator. It's between 1.081895 and 1.083019. Okay. So notice that it may be helpful to have a calculator to do some of these estimates within your homework problems, but anytime we would give you a problem with estimates on an exam or quiz, you might leave something in a form more like what we had above here. Okay, but we do get some bounds on the actual value, so that's a useful estimate for our sum.